That's right. I'm very excited to be here, and thank you so much for the invite. And thank you to all the organizers for a really great week. I am going to talk about the Klein 4 slices of integer suspensions of HF2. And this is all work with Bert Guillou. And we're very excited that our paper just appeared on the archive today. So if you would, it was perfect timing, pushing to the last minute. So if you'd like to see any details about the proof or more precise statements of results, you can check that out. So already this week, we've seen some really lovely talks that used the motivic slice filtration. But when I'm talking about slices today, I'm talking about equivariant slices. So the equivariant slice filtration, it is modeled on Vygotsky's motivic slice filtration, but there's definitely a lot of differences here. So I think the original inception is Dan Duggar's idea with the group C2, and then Hill, Hopkins, and Ravenel developed it for all groups, all compact Lie groups, in their solution to the Kervaire invariant-one paper. Yeah, so for the sake of Doug's health and the validity of some of my propositions, G will be finite. All right. And because we're working in the equivariant world, I am working with objects that are genuine G spectra. So when I write X here, I mean a genuine G spectrum. And I should also mention that the classical version is not really the one that I'm going to be looking at today. We're going to be using the regular slice filtration. So not only am I talking about the equivariant slice filtration, but I'm talking about the regular one that was developed by John Ullman. And I'm going to tell you precisely about that. Yes. All right.
Classical here is like 2009.
I know, right? I didn't actually want to use the word classical. I can blame that on Mike Hill. I think he put that in one of our papers. All right. So if you're not familiar with the equivariant slice filtration at all, what you should be thinking is that it's an equivariant analog of the Postnikov tower. And the Postnikov tower, we know it filters a spectrum by its homotopy group. So we're thinking about constructing it by killing maps from spheres. But in the equivariant setting, we're going to be using different spheres because we know in the equivariant world, we like to grade things on representations. So the categories that we're going to use to construct this filtration actually are generated by representation spheres of a certain form. So what do those look like? Well, I could take many copies of the regular representation for a subgroup H. But now these are H objects, and I really want to work in G spectra, so could induce these up. And if I take the localizing subcategory of G spectra generated by these objects, where I'm only going to take the ones where the dimension of the underlying sphere is greater than or equal to n, these form our categories tau greater than or equal to n, I'll just say tau n, that are the categories that we use to construct the equivariant slice filtration. So it is not triangulated. So this is a big difference between the motivic world and I guess maybe then the effective motivic slice filtration is maybe slightly more similar to what we're doing here. Yeah, okay, so by localizing subcategory, I am putting in cofibers and extensions, but there aren't any desuspensions allowed. I can suspend and I'll get to my next tau n categories, but yeah, I don't have a T structure and it's not triangulated. Yeah?
Do you mean what you wrote, or do you want to induce up the sphere from H to G? You want a G spectrum?
Yeah. Yes.
So
it's only an H spectrum, right?
G plus smashed up.
this is an H spectrum. Sorry?
The result should be a G spectrum, so don't you want to induce up from H to G?
That's what I'm doing. I guess, I don't know, do you want to, you could think about, like, I'm smashing
What's the G
over.
action on the right
He
hand
wants you
side?
to put the H under the smash.
Yeah, this is, yeah, so, okay.
Not isomorphic otherwise.
Does that make you,
A different thing now, yeah.
okay. So, all right. So, in any case, think about taking this H object and smashing over H up to G, and now we have a G spectrum. All right. So, here are our categories that we're going to use to construct the slice filtration. And so, associated to these localizing subcategories, so I guess here's kind of, maybe it's a bunch of definitions. Associated to tau n, we have a localization functor, Pn minus 1. So when we apply this functor to our G spectrum X, this is us essentially killing our maps from these spheres into X. And just a bit of notation that will be useful, and then I will put these together into a tower. When we are talking about objects that are actually in tau n's, we might write that x is greater than or equal to n. So this is exactly just notation to say that, that x is in tau n. So I guess what we're saying here is we're talking about kind of this idea of connectivity, but it's maybe a slice connectivity, right? So x is in these tau n's. But we have a corresponding maybe less than or equal to notion. And this would just mean that if we applied our functor to x, that we would have an equivalence from x to that functor applied to x. All right.
So if you have an x in tau bigger than or equal to n, and you apply the Pn minus 1 to it, it's 0. Or no?
Yeah. Yes.
Okay.
Yes. Okay. So these tau n's, because we've created them just based on dimensions, they include tau n into tau n plus 1, and so we get these natural transformations of our functors, and this is what's giving us the slice tower. So here, just as a reminder, we're working in the regular world. So the regular slice tower.
Excuse me, do you want to say x strictly less than n if that condition is satisfied? You don't want it to happen.
Yes. I guess I would, I could also do this and
Yes.
this.
Yes.
Yeah. All right. So all these natural transformations are going to fit together to form our tower. So I might have something like the n plus first mapping to the nth, and so on. And this is really constructing x in an analogous fashion to the Postnikov tower, in that if we look at the limit, we're going to have x, and if we look at the co-limit, we're going to have something contractible. But what we're going to really focus on today is kind of what's happening at each stage and keep track of the fibers, which we call slices. So I might write the fiber at each stage using upper n and lower n, or upper n plus 1 and lower n plus 1. And this object is what we refer to as the n slice of x. Okay. So what you might think then, in some sense, equivariantly, is that these n slices are kind of these homotopy building blocks of our G spectrum X. All right. So I wanted to just highlight some important and useful properties here. So the first important idea is kind of how we're really seeing equivariance here. So we've built things out of all of these H objects induced up to G objects, and if we kind of forget down to each subgroup H, we're actually going to recover the slice tower for a subgroup H. So if I write this kind of I star H as I'm taking some G spectrum and I'm thinking about it as an H spectrum, if I apply that to the tower, I will actually get the tower for X thought of as an H spectrum. So this is quite nice. And in fact, if you let H be the trivial group, you actually recover the Postnikov tower. All right, so that's one nice property. Something that you might wonder, if I keep kind of making this analogy to the Postnikov tower, is how suspensions play here. Well, these categories are a bit tricky. If I suspend objects in tau n, I will land in the next tau, n plus 1, but I don't get an equivalence of categories there. So in fact, it is not the case in general that suspending my tower would result in the tower of the suspension. That's not true. But what were we using? We weren't using trivial spheres at all. We were using regular representation spheres. So if I use the regular representation for G, that will induce equivalences between tau n categories, tau n to one that is the size of the group higher. So while that one is not true in general, if I were to suspend by rho, where I'm thinking the regular representation of G, this will be equivalent to the tower for the Roth suspension of my spectrum. Okay, so that's nice. Something else that I mentioned when I was giving notation over here is that when we write something like this, we're giving this idea of connectivity. Right? We're saying x is greater than or equal to n when it's living in this tau. We have some idea of n connectivity. But it's not the same. When we say slice connectivity, we're saying that because the objects that we use in here are often less than n connected. So for G spectrum X, when we write this and we're saying X is in tau n, what is this really the same as? Well, there's a couple ways that you can think about it. So one is that actually this has a nice relationship with the connectivity of the geometric fixed points of the spectrum. So if I take the geometric fixed points for any subgroup H, I find out that this is n over the size of H minus 1 connected in the classical sense for all subgroups of G. And in fact, if n is non-negative, this works for ordinary fixed points. And I think this was first done by John Ullman. And all of that's the same. It's the exact same connectivity. Okay, so I mean, I think then it's clear when we have this notion of connectivity here that those objects really are less than n connected. So what does this mean when we're talking about the building blocks or the slices? what's an n slice really encoding? It's kind of encoding the difference between the nth object in our tower and the n minus first object in our tower. But if we're killing maps from objects that are less than n connected, things get kind of messy, right? So we're not seeing kind of the true Postnikov layer where we have that the fiber is just one non-trivial homotopy group. In some cases, it actually is that nice. So let me just mention a couple. And I'm translating their original result to the regular world. But what does this say? If we're thinking about 0 slices, right, so we'd be thinking about the 0 slice, and this is p0 to p minus 1. And those objects really are as connected as we expect them to be. And so, in fact, the 0 slice is really encoding the 0th homotopy group of our object in dimension 0. So, in general, 0 slices are really the same things as Eilenberg-MacLane spectra associated to Mackey functors. So I'll say a little more about Mackey functors, but you can think about this in the sense that Anna Marie and Tina have been talking about, and I use this underline to denote it. In general, 0 slices are Eilenberg-MacLane spectra, but more precisely, if I wanted to describe the 0 slice of a G spectrum, it would be the Eilenberg-MacLane spectrum that comes from the 0th equivariant homotopy group of our spectrum X. Okay.
Is that an actual equivalent to model category? Just a rough description.
Are you saying that the heart of the T structure is the category of negative?
There is no T structure. Yeah, they're not. I know it's hard when you're using that analogy. The category of 0 slices is really equivalent to the category of Eilenberg-MacLane spectra from Mackey functors.
What's the thing that fails compared to T structure?
You can't desuspend. Because if you take little desuspensions of those regular representation spheres, those are no longer objects in those tau n categories.
Any category shows co-elements and extensions gives you
It's also one confusing.
What?
If you're generated by something, don't you always get a T structure?
suspension of tau less than or equal to n is not tau less than or equal to n plus 1.
Oh, you're doing the Tn's independently of each other.
Yes.
Not the 0.
Yeah, you generate them individually. Okay. Are we happy enough? Okay. All right. So when we are thinking about things in kind of maybe small positive values of n, it's not so complicated. But if you think about letting n even just be 1, then what starts happening is you end up with things that maybe are slightly less connected than you expect. But it actually doesn't change too much. You still do have Eilenberg-MacLane spectra that have been shifted up by 1. But here I'll write this twiddle to denote that we're not taking all possible G Mackey functors. We're only going to take Mackey functors where the restriction maps are injective. Okay. And so what that means more precisely for a particular G spectrum X is that the one slice of X is the Eilenberg-MacLane spectrum of the first homotopy of X, where you've quotiented to make those restriction maps injective, and then you've shifted up 1 dimension. Okay. Now, if this kind of story continued where all of our slices were Eilenberg-MacLane spectra,
Are you saying that the inclusion of those Mackey functors has left the joint, or what do you mean by quotient?
Oh, so I guess I'm thinking about it as if you think about a Mackey functor in kind of the way that Tina was defining it first, where we have all of these groups and restriction and transfer maps in between them. I'm quotienting at each group level in a minimal way so that my restriction maps all end up being injective.
Quotient did something in the bottom also, so why is it injected now?
You quotient out
Well,
the kernels of restriction maps.
Yeah, right. And if the bottom, if you were thinking about this kind of thing where the bottom ended up being 0, then it would.
It's a Mackey ideal.
Yeah.
You don't do anything to the bottom.
Right, and and I guess I was something that I found helpful is you see that if the bottom group really were trivial, that you end up having to kill everything. Okay.
Being a module over constant HC constant?
I'm not sure. I guess maybe modules that Mackey functors that are modules over the constant z do satisfy this, but I'm not sure if all.
It's not the same.
Yeah. Okay. Thanks, Dylan. All right. So if this story of higher and higher slices being Eilenberg-MacLane spectra, if that was the case, I think we would have computed most things by now, but that's not the case. So in general, let's say n slices for n bigger than 1 are not of the form sigma n hm for some Mackey functor m. There are some that are, but certainly not all. To give you a more precise example, I want to zoom in on just using a particular group for a bit. So we will work with our favorite group, C2. So what's going on when we think about just the group C2 equivariantly? Well, we are working with, we'll start with ideas of representations and Mackey functors. So in C2, my regular representation, it's of dimension 2, and it just has 2 pieces, 2 irreducible subrepresentations, the trivial and the sign representation. Also, if I wanted to think about a Mackey functor on C2, well, I really just have to describe what happens on orbits and then the restriction and transfer maps. So I'm going to use Lewis diagrams to depict Mackey functors in this talk. And so we would just have to say what happens on C2 mod C2, what happens on C2 mod E, what are these groups, and then we have the restriction map and the transfer map. And those pieces of information would completely describe a C2 Mackey functor.
You also have an action on the bottom.
Oh, yes, I'm sorry. I'm quite sloppy because all the Mackey functors that we end up looking at have trivial vial action. So you're correct. We also have the action of the vial group. At each level. But I will not say any more about vial actions because all the examples I'll do for you today have trivial vial action. All right. So let me just write maybe 2 quick examples of Mackey functors, and then we can get back to slices. So Mackey functors that are going to be important for us today, we're going to work in F2 instead of in the integer z, but the constant Mackey functor works in the same way where we're saying that every object is just F2. And the restriction maps, or the restriction map, is the identity, and the transfer map is 0. And another Mackey functor, there really aren't so many very interesting ones we could talk about, but another one that will show up for us, I'll write little g. And on C2, mod C2, it's F2. And on the underlying part, it's trivial. And the reason that g is chosen is that we would say that this Mackey functor is geometric. In that its corresponding Eilenberg-MacLane spectrum is a geometric spectra. And it really doesn't see what's happening down below. All of its information is encoded in the fixed points. Okay, so back to slices. Maybe I should give you a specific example of why n slices are not always of this form. If we were to take the row suspension of HF2, well, we know HF2 is a 0 slice, and we know that suspending by row preserves the slice tower. So here row is of dimension 2, so what we've produced is a 2 slice. But I guess if we were to maybe even just look at the nice picture that Mark gave us for computing ROG graded homotopy here, we would see that we have 2 non-trivial homotopy groups, so this is not an Eilenberg-MacLane spectrum. Sorry?
Minus row shift.
Yeah, so you're right. If I minus row shift, then it is. But I guess for us, we'll just take this to mean that we have more than one non-trivial homotopy group. Yeah. Okay. In the group C2, though, we actually can compute everything. So let's see. We already know about 0 and 1 slices, and we know that suspending by row preserves our slice tower. So this is enough to determine all slices for any C2 spectrum. So if X is any C2 spectrum, then, well, we can take X and we can, as Mark is pointing out, we can desuspend and pick up some nice information of the 0 and the 1 slices, and then resuspend to get the entire tower. And so what that means for us is that we have two flavors of slices. We'll have even slices, which come from the suspensions of 0 slices, and we'll have odd slices, which come from the suspensions of 1 slices. So here, we have that all of our even slices are just k-row suspensions of the k-roth homotopy of X, and odd slices are the k-row plus first suspension of the k-roth homotopy after we force restriction maps to be injective. Okay. So specifically, if I were to plug in just the spectrum HF2 or maybe integer suspensions here. So let's say, I'll put it here so we can save it. If I have integer suspensions for HF2, where my group is C2, well, it's really just determined by what my k-row homotopy groups are of HF2. Oh, and I should underline. So what happens, if you look at those homotopy groups, you have homotopy in dimension n, and you have homotopy in some range of groups, but actually all those homotopy groups are the geometric Mackey functor. And so we're not going to end up with any odd slices, because if we make our restriction maps injective in that geometric Mackey functor, those become trivial. So the non-trivial slices here happen only in dimension n. And in fact, this n-dimensional slice, it is just a shift of HF2 where the dimension is n. And we know exactly the representation is whichever one of these, depending on the parity of n. And then our 2k slices, well, they would all be k row shifts of h little g. But in fact, our geometric Mackey functors, they can't see what's happening to those sign representations. And so this is actually just the same as the kth suspension of h little g. And these only appear in a certain range. Okay.
Carolyn, did you mean the odd slice to be pi k rho plus 1 over there in the middle board?
I did. Thanks, Doug. Yeah, thank you. Okay. So, great. We have our entire picture of what happens when X is a C2 spectrum, and if we pick particular C2 spectra, we can compute the slices explicitly. Well, what other slices do we know about? So I'll just make some mentions of other things that we know. So, right, so C2 is very special, and we can describe all of the slices. We can in some other cases too. And so just kind of a brief mention of some of these. If we have actually the cyclic group of order p, where p is an odd prime, we have a similar description of all slices, like we had here, based on 0, 1, and in fact we have a description of -1 slices. But I'll just say similar description of all slices.
So could I ask about the first, when you said PNN of X, what you meant? Those two, that line and the following line don't seem to be consistent.
I did mean this, that the nth slice is a special one, and it's of this form where we're actually seeing the constant Mackey functor, but then all the other higher slices are these geometric ones. Yeah. All right. So when G is CP, we have a similar description of slices. I would say maybe if we take CP and instead think about any group, Dylan gave a nice description of the slice categories. So is it any group, Dylan?
Well, groups are finite, right?
Yeah, groups are finite. That's right. Yeah. So there's an algebraic description of slice categories. All right.
What does that mean, algebraic description?
You can look up Dylan's isotropic n spheres and slice spheres.
What kind of statement is it?
Ask me about it later.
Ask Dylan about it, yeah. Okay, so this is about slices in general, but I'm going to start focusing on kind of what happens, at least when X is some kind of Eilenberg-MacLane spectrum or a suspension. And in that case, we do have a full picture of what happens for cyclic P groups. So I guess we knew what happened for the integer suspensions and kind of these lambda suspensions, which were kind of two opposite pictures. But then Ming-Kong Zhang came along and just did all ROG graded suspensions. So V is any ROG suspension. Okay, great. But in terms of getting these kind of like very precise descriptions of what these slices are, we decided to explore a different group that's not cyclic.
Carolyn, I can only do CP squared.
Oh, that's right. Sorry, Ming Kong. Thank you. All right. So for the rest of the time, our group will be the Klein 4 group, and actually I will just write K to denote it. Okay, so what objects do we have here? Ooh, and actually I'll write these here and we can save them. So inside of our Klein 4 group, we have 3 subgroups of size 2, and I'll denote these L, D, and R. All right. So in terms of the representations, if we're thinking about the regular representation here, now instead of having 1 sign representation, we have 3 sign representations, one that fixes each of these. And I'll just write them alpha, beta, and gamma. It won't actually matter too much. But the important part is that we have this regular representation of size 4. If we restrict down to thinking about what's happening on C2, we end up with 2 copies of the regular representation there. And we know what happens on fixed points, and I think that's probably enough to say what I want to today.
So when you say restricted CP, you mean any of the LPI?
Yes, yeah, that's exactly. If I'm not being picky about which one, things are very symmetric, so it doesn't matter which one, yeah. All right, so then we also need to think about our Mackey functors. For C2, that was really simple, right? We just had 2 orbits to consider, and now we have 5. Counting, okay. So for Mackey functors, right, we have what's happening up at our group K, not G, and then at each subgroup, and then at the trivial one. So rather than write all of those, I'm just going to give you an example and tell you explicitly the constant Mackey functor for F2 here is that we have an F2 at the level of K, and we have an F2 at each subgroup, and we have an F2 on that underlying orbit, and all of our restriction maps, just like in the C2 case, are the identity. And I'm lazy, so all transfer maps that would go back the other way are trivial. Okay. But any Mackey functor that we have here, we can depict in some similar sort of diagram. Okay. So let me state kind of an overview of our result, and then we'll dig into why does it make sense and what's really going on with it. So for n greater than or equal to 5, we have a complete description of the non-trivial slices, or, well, of the slices of the nth suspension of HF2. Okay. So they are all representation suspensions of Eilenberg-MacLane spectra associated to Mackey functors. And based on which slice we're at, these vary. So I don't know if this is very terrible notation. Please excuse me. But for each I, we could say what is that representation V that we're suspending by, and what is the explicit Mackey functor that we're seeing. And they're only appearing in certain dimensions. So maybe I'll say, at the very least, well, the size of V is actually the dimension of the slice that we're at. And this is only going to happen when I is n. So kind of like in our C2 case, we had this n slice, and then we had a bunch of higher slices. And we have that here, but not for all values of I. There it was just for even values, and here it's the same thing. But they appear in slightly different flavors. So we'll say when I is 0 mod 4, and when I is 2 mod 4. And the 2 mod 4 slices happen in the range from n to 2n minus 4. And the 0 mod 4 slices go up to 4n minus 12. I'm sorry, Doug, did you have a question? Okay. All right. So this is just kind of saying, if you squint at what's happening, we know the form that the slices are taking and where they are appearing. So now I should spend some time telling you, one, why does this make sense, that these are where they appear? And then two, kind of what are these V's, what are these M's? What can we say about them?
So is there nothing for odd I? Is that the deal?
So there is nothing for odd I. That is the deal, yeah. Except for the n one, when n is odd. So let me just give kind of two overarching ideas of kind of where some of this is coming from. And the two ideas are this. On the one hand, we know that C2 is a subgroup several times over in our group G, and we know about restriction. So if we look at what's happening, so maybe let's say this, we know the C2 story. That's nice. But then we also have a nice computation of Holler-Kriz that gave us, maybe I'll say, the ROG graded homotopy groups of HF2. Oh, I am wrong. Just on the G fixed points. There we go. So we're coming into this with a complete knowledge of what happens on subgroups and a knowledge of homotopy on the G fixed points. And so there's some idea of, okay, maybe we can merge these two things together. Oh, yes, thank you, K. I'm still getting used to that. Thanks, John. All right. And then the other part that goes into the ideas here, we've already seen before, and that's really, what did we do here? We knew about 0 and 1 slices, and we gathered that information, and then we bumped things up. We also know about 0 and 1 slices, and we know about some other, maybe we'll say lower dimensional, easier to compute slices, and then we have some results of suspensions that will bring us up to levels that we want. So maybe I'll say lower dimensional slices plus suspensions. Okay. And maybe this would have been a better answer to the question how, but okay. So let's use some of these things. So as Doug pointed out, we don't have any odd dimensional slices, and why does that make sense? Well, on the one hand, I think these slices, the n and then the ones that go from n to 2n minus 4, look very familiar to us because those were exactly the slices that we saw for C2. So when we restrict to C2, what we're seeing is, well, we're seeing an n slice, and we're seeing even slices in the range from n plus 1 to 2n minus 4. So that tells us that we should have non-trivial slices in those dimensions as well. And it also tells us some idea about the Mackey functors here, in that when we look at C2, so when we look at L or D or R, we should be seeing those little geometric Mackey functors. So our M's here should have F's in our subgroups of size 2 and a 0 down at the bottom, and, you know, well, maybe we don't know the K fixed point story just yet, but we have this idea. And then what else? Well, when we restrict to C2, anything that was trivial on C2, we're not going to see anymore, right? But there could have been many slices that had K fixed point information, but nothing else below that would restrict to trivial things. So what does that tell us? It tells us that our other slices are geometric. So remember, I was saying geometric is what we use to talk about things that have only the whole group fixed point information and nothing below it. So when we restrict to C2, anything that we see these, anything else that we don't see had to be geometric. But we actually know some nice things about geometric slices, namely that those can only occur in multiples of the dimension of the group. So these give us our 4K slices. And, well, they have nothing below. They have just some information on fixed points, but maybe we don't know exactly. So I'll write like a little g to a question mark to say, okay, there's something happening for our geometric Mackey functor, but maybe we don't quite know what it is yet. In terms of this range, so these are our 4K slices, or 0 mod 4 slices. The upper bound here is really just an argument about homotopy groups, and it's maybe not very enlightening, but it can be shown that that's where actually the slices stop. And in general, it kind of seems to be, and I don't know, maybe like Min Kong can confirm, but the kind of the top slices that we're seeing are usually in some multiple of the order of the group size. It's like the size of the group times the suspension here, and then maybe shifted down a little bit to deal with some sticky issues. Okay. When did I actually begin, Julie? Thank you. All right. So, right. So, kind of what I was telling you here was really just all about, well, we knew the C2 story, and then maybe we knew some properties of geometric objects. And then all of these question marks, these can be taken care of from Holler-Kriz. So everything that's happening on top is just G fixed point information. So in particular, we already knew that 4K slices, so maybe I should be a little bit more precise here. We would know in general that 4K slices for the Klein 4 group would be like 2K slices for the C2 group, where we're taking our 0 slices and we're bumping them up. So here, we really did know that we should have, you know, the K row suspension of the K row homotopy. But since our objects, we know they're going to be geometric, to compute this, it really was enough to know what was happening at K fixed points, and that gave us the complete story about 4K slices. All right. The n slice and the maybe 2 mod 4 slices. These are a little bit more odd because we don't know what 2 slices look like in general, so to come up with all the 4k plus 2 slices is not an easy thing to do usually, but that's where this story kind of comes in, that computing a few lower dimensional slices and combining with some idea of suspension would get us what we want. So I'll give you the idea of that suspension, and then I'll show you some diagrams. So maybe I'll just say here, 4k plus 2 slices, or n slices. We would use a fact that suspending with rho is great and it tells us the whole story, but it actually also tells us a little bit more information just in certain integer suspensions. So in fact, if I wanted a slice, oh, I should use I, huh? If I wanted the I slice of my spectrum, it turns out that this is actually the same as suspending this is right. I minus 4. Right. So it's not that I'm shifting by rho on my spectrum. I'm shifting my tower by rho, but that's the same actually as shifting certain slices by dimension 4, and this is only in a particular range. Okay. But it suffices to say that if you compute a couple things and you have this kind of freedom to suspend by 4 to pick up the next ones, you can make some kind of recursive argument that will pick up higher and higher slices, at least kind of in the range that we need them for these even slices that aren't multiples of 4. Okay. So maybe I got a little excited telling you all of these things, so now I'll just show you some pictures to give you kind of a visual of what's appearing. So what I'm going to be putting up here are some spectral sequence diagrams for particular suspensions. And we'll start off with, in case it's hard to read, the 8th suspension. And so what I have here is, well, of course, the smaller one is our slice spectral sequence for the 8th suspension when we're using the group C2, and then this larger one is when we're thinking about the entire Klein 4 group. So for the slice spectral sequence, what we're seeing here are the homotopy groups of our slices, and if we run through all the pages, we converge to the homotopy of our spectrum, which will be really simple for our case. And the homotopy of the slices appear along diagonals. So right here at the bottom, this is our bottom slice, our n slice, in this case our 8 slice, and these are the 4 homotopy groups that we have. And then higher and higher we have all of our other 2 mod 4 and 0 mod 4 slices. And the ones that are, most of these solid ones, these are kind of those Mackey functors that are going to restrict down to non-trivial things on C2. So on those subgroups, those Mackey functors are non-trivial. Whereas all these ones, all these circles or the tiny dots, those are all geometric Mackey functors. And it might be hard to see the numbers in here. There's just different numbers in these circles to tell you how many copies of F you have in that geometric Mackey functor. But I think we can see that, right, these kind of solid-looking ones here, when we restrict down to C2, we see exactly those. All right, so this is a bit crazy looking, but this is, oh, I don't know, it's so tiny. The 18th suspension, maybe that's right. But I wanted to show you it because I think you can see really easily we have this bottom end slice. All the other slices are of higher dimensions. And then it's easier to see in this kind of big diagram that we also have this is the demonstration of the vanishing line. So because we have these notions of connectivity, we actually have this line of slope g, or size g minus 1, that we won't have any homotopy groups of slices above that, so that's where that stops. And then I wanted to, I guess, show you kind of how the spectral sequence is working here. So here's the 12th suspension of HF2 for our Klein 4 group. And again, we have this bottom slice, always this N slice has very interesting homotopy. And then we do have some of those 2 mod 4 slices here that also have not completely geometric Mackey functors. And then everything above, these are the things past the point that C2 can see anything. So these are just geometric objects, and so they have only one non-trivial homotopy group. And you can see early on which slices are going to be affecting other ones in terms of which support differentials. And so kind of, I mean, what you can see early on, too, is that there's really a lot of interaction. It's not like one slice is killing things at a time, or I guess I should say in each layer we're kind of affecting higher and lower homotopy groups at one time, and then as you run through, you know, everything should die out because we have such a nice homotopy group in just one dimension. All right, so I'll stop there.
Make use of this restriction to these 3 copies of F2, and then it sort of hit me, well, wait, this has to be sort of symmetric under the, well, the permutation, which actually is the same as an action of GL2 on the Klein 4 group. Now, I don't, it seems like that would be used, so your Mackey functors are sort of symmetric, are invariant under, that appear, so that probably something to be used. I don't know if it would help you with those the white dots that you had as opposed to the black dots. The black dots are probably the easier ones to figure out.
Yeah, in terms of which ones are going to support which.
Yeah, but it seems like you would have an action of the general linear group on the Mackey functor, right? By symmetry or something, you know.
Yeah.
So this should be a tool to use. Maybe it's on Mackey functors that can appear or something. I don't know.
That's an interesting idea. Yeah, I'm not sure. I mean, I don't know if this is related at all, but I mean, we were working with like a suspension that was completely symmetric in terms of what was happening because it was just integral suspensions. But definitely when you start, if you wanted to think about slices for things where you just suspended by some of these, you end up with a lot of Mackey functors that aren't symmetric, and then maybe that becomes useful there. Yeah. Yeah.
Your pictures look very cool, and there appears from far away here to be some kind of like symmetry along the middle.
Yeah.
I don't know why that is.
That's a really good question, Vesna. So do you mean like kind of the diamond that's appear? Yeah. Oh yes, of course. So yeah, right. So this is, I think, this like in between. I actually don't know exactly about the symmetry, but what is kind of happening in this middle portion is that this is where we have 2 mod 4 and 0 mod 4 slices together. So we have geometric and non-geometric things, and I don't know exactly. I guess there is also something like our 2 slices also ended up being of a very nice form where the Mackey functors used didn't have any geometric part. So it might be something about the geometric things and these things that have no fixed points fitting together. But yeah, it looks nice. Yes?
Do you have any ideas about slices for sphere spectra?
Oh. That's a good question.
Or, I mean, relations with other spectral sequences?
I don't think I could say anything intelligent right now.
That's in the future.
Yeah. Ask somebody at this conference in 10 years. I don't know.
All right, and we now have a coffee break. So let's resume at 11:40, and let's thank Carolyn.